Right. Actually, that is a central theme of my work. Uh, in practice, we have first worked on lakes, and the general idea of a critical point is that if you change gradually the conditions of the systems, when it reaches a critical point, very little is needed to make it tip into a completely different state. In the case of lakes, we've seen that they can tip from a clear to a turbid state, for instance. But the latest thing that we're working on now is the onset of migraine attacks, which are also critical transitions, but in the brain tissue. Well, emergence is one of the most fascinating aspects in dynamical systems. You know the rules of the parts of the system, and yet a very surprising pattern emerges. In my own personal work, the most important example of emergence that I have been focusing on is emergence in evolution. We have built artificial worlds in the computer and simulated evolution of hypothetical organisms. And what we see is an emergence of a self-organized pattern in which you get groups of species that basically do the same thing in life. They take the same ecological niche, self-organized niche. So we think that if you look at nature, at the species, that there are countless species, but actually they are grouped into a limited number of emerging similar kinds of organisms. I'm studying both ecosystems and social systems, and there you see an important difference. In ecosystems, you can usually reverse the change, like if a lake that was clear becomes turbid, you can usually reverse that change. In human systems, you can never really reverse the change because people learn over time, things change. History never repeats. It never repeats, although some aspects do repeat, like we see conflicts arising with the same kinds of dynamics over and over. Now, I must say that in the ecological systems, evolution doesn't happen on the ecological timescale, as we say. But if you look at millions of years, then you have, of course, evolution. The species evolve, and because of that, the rules of the game evolve, and history never repeats. So it's an interesting balance there. Evolution makes things never repeat, although some rules stay in the system. Yeah, heterogeneity can arise from different sources. It can come from within the system. So like in the case of the self-organized patterns or self-organized fluctuations. But most systems also are exposed to heterogeneous environment. And actually, when you have a heterogeneity in the environment, in general, it tends somehow to smooth out most of the cycles, dynamics that you expect to be self-organized in the systems. On the other hand, sometimes heterogeneity can actually be amplified by the system. For instance, if a system tends to have a cycle or produce chaos, but it just doesn't do it by itself. If you push it a little bit by some fluctuations in the environment, it may be boosted. So the interaction between external heterogeneity, spatial or temporal, and what happens within the system makes things really complex indeed. If you play with models of the interactions of predators and prey, you very easily get cycles and chaos in predictable behavior. And actually we have recently shown that in reality that also happens. We have shown that by locking a system, a plankton system, into a container, the work of a German collaborator looking for 10 years what happens when you have this system exposed to a constant environment. And what appeared is that the system keeps changing over time. And we could show mathematically that this is chaos. So chaos happens in nature. And that means unpredictability on the long term, but only of the details. And we can still say, for instance, what are the conditions for a lake to become green with phytoplankton? Even though we cannot predict which species will be abundant, because on that more detailed level, the dynamics are chaotic. But that doesn't prevent us from predicting the larger patterns that are actually quite regular.